Dear viewers, today we are going to have a look at the practical implementation of NAND as universal logic gates. So let's again recapitulate what we have seen earlier. We have seen earlier that to prove NAND as universal gate, we first need to construct OR and NOT. That is, we have to realize the functions OR and NOT. So to start with and to begin with, we will first try to realize the NOT function using NAND gates. So first of all, what we need to do is we need to get the expression of a NOT function, and we know that is it is, let us assume y to be the output, then a is the input, then as per the symbolic representation, this is the input, this is the output, and this is the Boolean expression. And to implement this, we will just have to extend this, and we will have to take a NAND gate, tie both the inputs together, and denote that as A, and the output will be A and A whole bar. So to implement this using logic gates, we will have to use a 7400 series, and 7400 series is having quad NAND 2 inputs. That means there are 4 NAND gates inside. As you can see, the inputs are given at 1 2 3 is the output, 4 5 6 is the output, and for the other one 9 10 8 is the output. 12 and 13 are the input, and 11 is the output. We have to remember one thing: to identify the pin number 1, we need to search for a notch or a dot. Here we can see a dot is available, so this is pin number 1, and then start counting anti-clockwise. Now in this case, pin number 14 is the supply pin. The maximum allowable voltage is +5, and it should be pure DC regulated. And then we have the ground, which is connected to the 7th pin. So let's see how we do it. Now first of all, connect the VCC to +5, then connect the ground, that is the pin number 7, to 0 volt of the power supply, or the return line of the power supply, and then connect pin 1 and 2 together to form a NOT gate. Label that as A, and pin number 3 will act as your output. Now you can use a digital multimeter, set the range to 20 volts DC, then apply a logic here, that is connect this either to +5 or to ground, and then check the output. You'll be able to see that this particular circuit behaves as a NOT gate. Now similarly, let's go for the next one and try to realize the AND function using NAND logic gates. We know the expression for AND is y equal to A and B. Now we can use a double negation, and using the double negation property, this means it is the same. Now we can implement this using 2 NAND gates. Let's see how we do it. Let us first label the inputs as A and B. So at the output we will get y equal to A dot B bar. Then we will tie both the inputs of the other NAND gate, and the output we will get is A dot B double bar. Now let's see how can we realize this using a integrated circuit. Now we again use the same integrated circuit, that is 7400. Then we will connect the VCC to +5, connect the ground to 0, connect select pin number 1 and pin number 2 as A and B. These are the 2 inputs. Then tie the pin number 4 and 5 together. This will make this one as the NOT gate. We are actually trying to implement this. Now you establish the connection between the output of the first NAND gate and the second NAND gate. That is, we will connect the output pin 3, 2, 4 and 5 like this, and now the pin number 6 will act as your output. We have to remember one thing, that output can be measured using again a digital multimeter. So what you'll have to do is you will have to connect the wires that are connected here. Following all the four combinations, like first you use this to connect it to ground, it will be 0 0, connect any one to plus 5, it will be 0 1, then vice versa, and the last one connect both them together to plus 5. So this will actually create a circuit which will realize the AND function. Now let us move on to the next, where we are trying to realize the OR function using NAND gate. Here again we know the expression as y equal to a or b, use double negation and then use De Morgan's theorem to actually switch this circuit from OR to AND. See, we have a AND operator here. Now we will implement this using NAND gates. Here we will use one inverter, another inverter using constructed out of NAND gate, and finally we will put that into another NAND gate to get the final output. So let's see, the first one is A, tied together we get A bar, then we have B, tied together we get B bar, and then again these two are put into another NAND gate and we get the final expression, which is nothing but OR gate. Now let's see how we do it practically. You use the integrated circuit, again connect the supply to plus 5 and ground, then tie the 1 and 2 pin, denote this as A, tie the pin number 4 and 5, denote that as B, then you connect the output of this to one of the inputs of another NAND gate, say it is connected between 3 to 10, then connect the pin number 6 to the same NAND gate to the pin number 9, and now you just take this as your output. Now again you can see we have created two NOT gates using these two NAND gates as shown here. Then we have the final NAND gate as shown here, and the output is from the pin number 8. Now again you have to apply all the possible combinations at this input and you will get the output here, which will give you a truth table showing it is acting as a OR gate. So let's conclude this session. Let's draw the conclusion. Here we have studied how to create OR logic, AND logic, and NAND logic, NOT logic using NAND gates, and we have also seen the physical implementation. How can we physically implement the functions using the NAND integrated circuit, that is 7400. So thank you very much for watching this video. You can tune in for other videos which will be related to practical implementation of all basic functions using NOR gates. Then we will have videos on half adders, full subtractor, full adder, half adder, then adders using multiplexer, decoders, and so on. So thank you for watching this video.